Maxime Agostini, CEO and co-founder of Sarus. Sarus is a privacy technology company, and we're going to discuss how to solve the question of making private data available for data science and AI at scale in the lakehouse. We'll see that there's not going to be like a single solution that solves everything, but by combining the right solutions, you can achieve something that's both practical and safe. The problem we want to solve is when you have tons of personal data or confidential data that you want to protect. But you also want to leverage it for your data and AI projects. So typically it looks like this. You have a set of tables with, let's say, individuals in them, and there's a lot of information about them. And on the other side, you have the data scientists and the analysts. What they want to do is learn something from that data, which is maybe they're building a machine learning model. Maybe they're doing statistics, extracting insights. In all of those objectives, they don't really care about like one individual. They just want to be able to use the data that's sensitive and extract some knowledge that is not sensitive. But to get from the left to the right, we need to solve the problem of can we protect the data along the way? The easy answer is let's just anonymize it, and then we're done. I mean, we've solved the privacy risk. But let's take a look at what that looks like. Regulators here give us a useful definition of what anonymization is, and they don't really tell you how to do it, but they tell you what not to do. And specifically, they say, well, anonymous information is not personal information. So far, so good. And to know whether you are personal information, you have to look at whether you can relate it to an individual. But here, there's an interesting aspect, which is how can you relate it? Like, what could you use to relate a piece of information to someone? And GDPR makes it clear that the use of additional information should be taken into account. So if by using additional information, I can relate some information to someone, then you can consider it anonymous. CCPA, you see the same kind of idea behind like indirectly linking information to someone. So when you want to anonymize something, you need to answer this question, can someone link that output to individuals? And to answer this question, you need to know what they might do. And especially you need to know what additional information they may possess to do it. They may possess like trivial things, like for example, if I know your name, I can trivially re-identify you in a database with your name. So, I mean, you'd probably want to remove the names. But if I know your email, same thing, like the obvious identifiers have been identified for a long time as a risk to anonymization. But what if I happen to know like transaction details? Maybe you're publishing something on Instagram, like you went to a restaurant, you take a picture. Well, now it's almost public information that you were in that restaurant that day. And maybe there's a series of events, like a series of posts on Instagram that become a fingerprint of you, and just like spending on those series of restaurants on those days become identifying. And this is public information here. It's on Instagram. So it's hard to argue that no attacker may ever use that information. It's public, it's out there. So you need to think about this when you try to anonymize data set. Like, can they possess this information? And here it's public. And worse, even worse, it might become public in the future. So how can you answer this question by knowing like what they might do in the future? You also, by the way, need to take into account additional computational means, which is another problem. So you see here, like, you need to answer a bunch of questions about like what an attacker may know if you want to be able to really clearly say that something is anonymous and be compliant with regulations. Well, it turns out that it's not just a theoretical problem. There's a bunch of papers on re-identification. This one, for example, showed that like with just 15 very high-level classifications, you could re-identify 99.98% of Americans. So it becomes like fingerprints of everyone. And you're talking here about very, very high-level things like just the race and maybe the state and a bunch of very high-level demographics. You can re-identify everyone. And there are funny stories like this one. Some of you may have heard of like the Netflix prize. If you're in the machine learning community, I'm sure you have, because it was, I think it was 2006 or 7. They had this contest where you were supposed to predict like what people may watch next. It was at the time it was DVDs, it was not streaming yet. And they had anonymized the data set. They had removed all names I named. There was nothing left in the data sets, just a series of movies people had watched and how many stars they had rated. At that time, you put stars on Netflix. And they had the contest, and someone won. It was $1 million prize. And unfortunately, a year after, there was this paper from University of Texas, where someone said, well, I re-identified like thousands of people in this data set. And the way they did it was by combining this anonymous data set with IMDb, very public. And on IMDb, like a bunch of people had rated movies as well. They had like commented, I watched this yesterday, and blah, 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 and I loved it, and didn't love it. And you could find like this fingerprint, like now the fingerprint was the series of movies you had watched, and it was public. So claiming that this data set was anonymous was not possible. So there was a lawsuit, like some people were offended that all of their movie history was on the internet, revealing, I don't know, like their preferences and so on. So they had to settle. We don't know how much it cost them. My bet is way more than $1 million. So we see here that like the idea that we can take a data set, make it anonymous, and then do our things as a data scientist or as an analyst is a bit like far-fetched. We can still like achieve something that would be anonymous under particular regulation. This is not like a goal that we can never obtain, but it requires an assessment every single time. You need to be very careful, like what are your assumptions, what is the attacker model that someone may do to re-identify someone. So if you share a data set with someone, like the Netflix data set, you need to state that you consider only people who might not like be combining things with IMDb. I don't know how you come up with those assessments, but like you have to do this if you want to be sure that it's locally anonymous to this particular use case. For this presentation, what matters here is that it doesn't scale. You can do it once, you can do it twice, but you cannot do it like all the time with all your data sets, with all the data use cases and all the different needs from your data practitioners that may be internal analysts or data scientists, maybe external partners, researchers. So we'll see if we can find a way to achieve this, and with something that's very important with people, for people working on the lakehouse is scale. So what do we want? As a data scientist, I want to see the data. I want to see what I'm working on. If I can't see the data, I'm probably not going to go very far in my data science pipeline. I want to be able to use all columns or as many as possible. I don't want to be working in a watered down data set where everything that's valuable to me has been removed. For example, if I'm working at Uber, I don't want to be working in a data set where someone has removed the pickup and destination. It would not be useful. I can't do anything with that. But of course, those are very identifying features. So most people, at least one of those is their home address. You want to be able to also do collaborations often. We talked yesterday about the Lakehouse federations. This is a big theme, trying to get more people to collaborate with data. This is something you want to do, and we'll see how to do it in a privacy-preserving manner. And finally, you want to be able to do that fast. You don't want to be waiting like months for some privacy review assessment or security review assessment every time you have a different need. So let's look at like the common answers to this, the traditional answers. So the first one we'll see two, and we'll see how we can try to navigate those and create a best of both worlds. The first one is to use access control. So sure enough, you can't anonymize the data set and forget about it, but for each use case, you can probably find a way to create an access role that works for that particular use case. So you can use access control. It's built in a Unity catalog, for example, or most databases. The idea is simple. I'm sure you're aware of it. Like you limit what people can access to particular rows or particular columns. Simple as that. You define the policies so that you can have those policies apply across the board And so you can scale that solution scale in the sense that you can deploy them to all the users, roles, across your entire data assets. And this is what it looks like. So it does achieve some of what we want to do. First, our data scientists, well, they can see what the data looks like. Not all of it. Some of it has been removed, but at least they have examples, so they can probably get started building their machine learning pipeline. Second, they have full flexibility. They can download their masked data. We talk about data masking. They can download masked data, and then it's on their computer, and they can use any library they want to use. They don't really have any control over this, but from their perspective, they're pretty happy about it. And you can have like fine-grained roles, like be very specific, like at a column level, with or without PII, and so on. I won't get into those details. But there's a bunch of cons as well that mean that we can't really achieve like the entire goal just with this. One of them is that they actually see the row-level data. And remember what we said, like the data cannot be made anonymous because they have access and they can download the row-level data. That means they're still left with the problem of, well, what they could do to re-identify if the data gets lost, if it's on the computer. Maybe it's misuse of data, maybe it's just compromised credentials, maybe it's just a data breach on their computer. So this is still like a liability you have to live with. The second one is, of course, like the columns are gone, trivially, so you can't use them. And you may not have reached like the level of anonymization or security that you want, so it's probably something that's going to be hard to use when working with external partners. It's more how you manage the accesses within your organizations under some trust assessment, like some trust models of what people may do internally, assuming that most of it is dealt with by the contract you have with your internal employees. It's not like a technical protection so much. So the main thing that doesn't scale here is that those roles need to be adapted for each use case. It's not even like attached to the data itself, because if you're using maybe you may not have the same roles for data scientists and analysts. You may not have the same roles for data scientists and analysts within the same department and from another department in your organization. It's definitely not going to have the same roles for people outside of your department in an external organization. So you need to review this. Those assessments are going to be per data set and per use case and per recipient of the data. Still haven't been able to fully scale, so let's move on. Second idea is the idea of the clean room. I'll picture like the high-level concept of a clean room, and we can go into some of the specificity of the clean room on Databricks. So the idea of a clean room is that put the data in a clean room, and the data scientists are outside of it, the analysts are outside of it. They can't really enter, they can't see the data itself. What they can do instead is that they can submit maybe a notebook that, if agreed by the data owner, can run, and they'll see the output. So this is pretty powerful because now instead of like sharing the input data, we're just sharing the output of a pre-agreed code. So in terms of amount of information that is leaving your systems, it's like much, much less. I mean, we're talking about like maybe on one side we have billions of records, and on the other side we're just sharing maybe the performance of a machine learning model that you wanted to validate, or the update of the weights. Maybe you're sharing just a number of patients that had a particular disease or something. So in terms of privacy protection, it's orders of magnitude better. So the pros are data scientists. They can see the data. So you've protected the data pretty well. That was an objective. We'll see that's also a shortcoming, of course. They can use data from multiple sources because you can restrict what they can do very precisely. It's okay to bring data from partners, even with IDs. You can have ID or any kind of identifier. Could be the emails and so on. You can bring those in, use those in your notebook to produce an output that someone agrees is safe. Put a stamp on it and you share it. So you can use a lot more data in the input because they won't be in the output anymore. In general, the concept of like restricting the privilege to the minimum, they share just the right amount of information. So in terms of privilege, you don't have the privilege to see the entire data set. You have restriction to the bare minimum, which is just the output. Of course, not seeing the row-level data is going to be an issue for our data scientists. But there's also the problem of the flexibility. They don't have the data on the computer, so they can't just try things. They have to ask every time they want to try like a new approach, a new machine learning approach, or maybe even just like a new dashboard, a new way to provide insights. They won't be able to do it on their own. They need to ask every time. And this process of asking needs to be pre-agreed every time. So maybe say, oh, that's not the notebook I wanted something slightly different. Let me try to aggregate things slightly differently. Well, that's a new review that's required. And by the way, this review is not trivial. I'm saying that, of course, the shared output is safe, but it's not as easy because you can't really tell just from one output whether there's a re-identification risk. And just to give you like one example to show that it's could be tricky is that say you're running your notebook and it's using fresh data. So you're refreshing the notebook. The notebook is authorized, so you can refresh anytime. Well, it turns out maybe it's just outputting some high-level statistics. Well, if you do it twice, like within like 5 minutes apart, there might be differences in your statistics by one person. It may or may not be a privacy liability. I don't know, it depends on the use case, but maybe the difference is a person who just entered the hospital and you just did a refresh between those 5 minutes, and now you know where that person fell in which bucket. So this like looking at a notebook and being sure it's privacy safe is not trivial. This is certainly possible, but you also still need to make assumptions. So and specifically for that last reason, clearly we still don't scale. We can't pretend we've fully scaled the way to interact with like data you can't see. So just to recap like what we have so far, in terms of seeing data, well, sharing filtered access, that has achieved some of it. And like the Data Cleanroom is not designed really to give you the way to feel and to touch the data. The ability to use all columns by design, like by definition, data masking does not achieve this. In Cleanroom, it could. You could consume many columns. I mean, it depends on how the notebook is structured. In terms of collaboration, it's probably hard with data masking by design. You don't want things to be matchable anymore because you don't want someone to bring their own IDs and combine things, and now they learn something about their users. So the first thing you'd probably remove is everything identifying. Notebook, that's something you can, Cleanroom, that's something you could do. In terms of flexibility, I mean, if I have data on my computer, I'm fully flexible. I can do whatever I want. If the data is still on the Cleanroom, well, each process requires pre-agreement. So let's see if we can get all four in a way that's fully scalable and repeatable. We're going to need a couple of ingredients. The first one is differential privacy. So some of you may have heard of it. I'm not going to do a full intro on this concept, but what's important to know about differential privacy is that we don't have a good definition of how to make input data anonymous. I just give you like some intuition of why. But we do have a good definition of how to make the output of a computation anonymous. This is called differential privacy, so this is not for the purpose of like having everyone fall asleep. The idea is that if you move an individual, like if their value moves, it should not transpire too much in the output. That's what this diagram is picturing. So this is the intuition of differential privacy. You should return noisy results, and the noise should cover the contribution of one person. So because we have a good definition of how to make outputs anonymous, this is something we want to use in automating the decision of letting people doing analytics or AI on our data. But differential privacy is not just like a little bit of a magic powder that you put on your data pipeline. We'll actually need something more. We need a way to take an entire pipeline, so maybe it's a SQL pipeline or maybe it's a machine learning pipeline, and to turn it into a version that protects privacy. So there's a bunch of reasons why differential privacy is actually a property of the entire computation. It's not something that you could put at the end of the pipeline. So we need to be able to map this kind of code, pretty straightforward code here that's predicting the income based on age and education, building a model with this objective. We need to turn not just the model itself, but the entire code into a version that's privacy preserving. So if we can do that automatically, then we can take a code, automatically make it privacy safe, and make sure that the output doesn't reveal anything on any individual. And finally, last but not least, we also need generative AI. The reason we need generative AI is there are some pipelines that we won't be able to make privacy safe. And think of a simple one, select star or data frame.head. Well, I can't just make that safe because I told you that I can't make the input data safe. But this is the first one, the first query we're ever going to get from our users. So we need a way to answer this. For this, we definitely need something. I mean, you've probably heard of synthetic data. So we need a generative model to produce fake data and make sure that this generative model is safe. By the way, to make sure the model itself is safe, you want to use differential privacy. If you don't, but that's like for another day. So with our three ingredients, let's see how we can combine like differential privacy, rewriting, synthetic data to solve our problem. The demo I'm going to do here is this intuition. This is a solution that we provide at Sarus, but there's other vendors that have a similar offering, where the data scientists don't have full access to the input data. Instead, they interact with the remote data through this API. Submit any job, so it could be select star, but it could also be a more complicated pipeline. And Sarus will rewrite this job into a privacy-safe variant and send it to the lakehouse. Get it executed and send the results back. In any job, I include like select star, like things like this. It needs to be seamless. It needs to be the same experience as before. So maybe the jobs come from Power BI, for example. So Power BI doesn't want to know about anything. They're just like sending SQL queries to the remote systems. So they want to send SQL queries to the Spark SQL API or the Databricks SQL API, and the first query we're going to get is going to be select star. So we want to be able to take those and pass them along. So without further ado, let's move to a quick demo. So the setup I have here, so here this is the admin UI of the Sarus software. We assume it's running on your cloud, so you have your data, and it's running on premise. We never have touched the data. We don't have to deal with personal data. And you have here a test, like a demo data set that's sitting on Databricks. So the data set is on Databricks, and for which we've onboarded it on the platform, and that would allow our data scientists to work on it. So I'm not doing the onboarding here because it triggers the generative AI model to be trained and so on, so it takes a bit of time. Just showing you here, we have the synthetic data ready, and we have the access roles ready as well. Here we have the data scientist who's here. They have a privacy policy that defines how they can access the data. The privacy policy is this one that says our data scientists are able to see synthetic data. They're able to see anything that's produced with differential privacy. For the experts, I can comment on the differential privacy parameters after the presentation. And they also say something interesting is that we're trusting our data scientists with models. So we say you have a special right to train a model. You can't see the data, you can't see statistics, you can't see any of that, but I trust you with a trained model. This is an exception. It's under the whitelisting category. And this is an exception that 99.99% of people make, by the way. They assume that trained models don't carry privacy risk. It's not strictly speaking true, but it's a reasonable assumption. So we're making this assumption here. Just want to make sure that it's an assumption that the data owner had to make. It's by default, it would have been protected. And now I'm going to switch to the other side, and I'm the data scientist. And I want to work on this data set here, where I can see my tables. So I'm going to do simple things, such as .head. And when you do a .head, well, what happens, you're not doing a .head on the data frame, the data that's in your notebook. There's never going to be any data in the notebook. The .head is a call to the SDK that has the exact same API as pandas or scikit-learn and so on. So it looks like you're working on a data frame, but actually you're working on a wrapped pandas data frame. And when you do the .head, the wrapper builds the computational graph, which is pretty straightforward here, is just .head. and sends it to the Sarus software. And the Sarus software looks at it and says, can't do .head with differential privacy, but I can still use the synthetic data. And you get the synthetic data result, which allows you to move forward. And then you can do things like compute a mean, for example. And when you do the mean, the same process happens. There's like a call to Sarus, say, I want the mean of that column. And then it's sent to Sarus, and so this one, we can use the real data for it. So we're going to use it with differential privacy. So this is to show the experience of working on the data you can't see. You can actually, it feels like you can see it because you can always look at it and you see the fake data instead. But at least you can make progress and iteratively just send queries such as .mean and so on. So here, I'm going to do a little bit more fancy here, where I'm going to build like an extraction using my 3 tables and select like the data set I want to work on. And I'm gonna, well, of course, then again, the first thing I want to do is a .head on that new data set because I did a SQL join, and I want to be make sure that this joint data makes sense. Well, here we're lucky that the synthetic data that has been generated took into account the foreign keys, so you can still join the various tables here. So when you do a join on the fake data, you get actually a completely formally correct response. So we keep building our system. We can, I don't know, count the uniques, count the missing value or DNAs here for each column. And I want to show you that we can go all the way to building actually a k-means model by doing some fancy pre-processing. So I'm just like running the comments here to go all the way to the last one, which is the evaluation of the fit-in model. So here you see something interesting is that last evaluation is whitelisted, which means that we're leveraging the exception we had to see trained models. We were not able to see the data, we're not able to see the means, we're not able to see any intermediary result, but we could still train a model and get like a fully trained model on the real data here because of this whitelist exception that I had. Just want to show you what actually those computational graphs look like. So it's something like this. So this is, I won't go into the details, but when we're talking about the model here at the end, it's actually the fruit of this entire computation that's been sent to the server, analyzed, checked against the privacy policy, and turned into a safe variant, in which case here it was a whitelist, so it just passed through. So what I wanted to picture here is how you can overcome the frustrations we had with the other 2 techniques. First, we're able to see data. Sure enough, we did not see the real data because that was a starting point. The real data was not available and could not be available to us. But we had something that's been built by a deep learning model using GenAI, so that is as close as possible to the real data. It has the exact right schema. It has the right relationship between the columns. So we can actually use that to prototype and test and build, whether it's dashboards or machine learning pipelines. We could use anything as input. Again, the protection comes in the output, whatever is in the input. That's the power of using differential privacy. It's the protection of the output no matter what the input is made of. You can still do collaborations, same spirit as any general data clean room. It's actually the automation layer on top of a data clean room. And finally, and I think that's probably the most important part, we have a way to automate the decision to assess whether the output is anonymous or not. Leveraging differential privacy, we can make this decision on the fly. It's not about like some internal privacy review by an expert that needs to decide whether that particular computation is safe or not. There's a mathematical guarantee here, and the most important part of the mathematical guarantee is not that it's more safe, it's not safer or more secure than previous decisions. It's just we can make this decision on the fly. So just in terms of integration, today we deploy on containers, whether Kubernetes or Docker containers. We are in the process of integrating directly as an app on Databricks, hopefully soon. And the idea is that it's the interface with all the applications that data scientists may use. So what I wanted to conclude on is that this is an illustration of like all the use cases where you have data, sensitive data, and you want to use it either internally, so within your organization, there's a lot of stakeholders that could want to have access to data. Talking about data democratization, one key component is it's fine to open data to everyone, but like how can you trust everyone to do anything with it? With a system like this, the data remains in the original infrastructure. No one has access to it. Every interaction with the data is logged and traceable. So you get like a much, much higher level of security, which actually empowers you to do data democratization as an organization. Also powers collaborations. You can make collaborations privacy safe because it's not because you work with an external party that you extend the risk to that other party. And finally, it's completely aligned with the objective of doing lakehouse federations, which were announced yesterday. So we have use cases, I'm sure you've thought of it, of healthcare, financial sector, whether pulling data from multiple parties or managing data exchanges between like hospitals and pharma companies. They all want to work together, but like the fact of sharing the data outside of the original organization is a challenge. It's both a regulatory challenge and an internal compliance challenge. Took the example of marketing and retail. There's other applications for sustainability. We're discussing minutes ago about like the application for using military data for health analysis and so on. So those are cases where data is very, very sensitive. And if you want to do something with it, you need to be extra cautious. So my final slide is really like, we try to solve data access and how to share data at scale. And actually the answer I came up with is like the best is just not to share data. If you don't share data, you're in a much better position to collaborate than if you try to do the sharing itself. So thank you very much. Maxime Agostini, I'm happy to take questions.